Okay, let us continue with the applications of the Rayleigh quotient theorem. So this next corollary that I'm going to talk about is going to be on block matrices, right? So suppose that you have a block matrix that's of the following type. We have a large square symmetric matrix on the top left, right? And then you have a vector y, a column vector y, and then you have the corresponding row vector y transpose, and you have a scalar r. Okay, so let's look at the structure of this matrix. You have a large n cross n symmetric matrix here, a column vector here, corresponding row vector, and a scalar. Okay, so this matrix is n plus 1 cross n plus 1 symmetric by construction. Okay, let's call this matrix A. Okay, so what I am going to talk about now is an application of the Rayleigh quotient theorem to understanding something about the eigenvalues of A as they relate to the eigenvalues of B. Now, why is this a useful thing to consider? Often in engineering, we may have to remove certain rows and certain columns of a matrix. For example, you have a matrix A that is n plus 1 cross n plus 1, and I decide to remove, let us say, the last row of A. That means I decide to remove this row. Okay, and to preserve symmetry, I decide to remove the corresponding column as well. The last column I remove, right? Then I'm left with this n cross n matrix B. So often of interest is, if I have done this operation of removing the rows, what happens to the corresponding eigenvalues? What have I done to the eigenvalues? A had certain set of eigenvalues to begin with. How have I modified that set by the action of removing these rows and columns? Okay, so that we are going to try to answer from the Rayleigh quotient theorem. Okay, so first some very elementary things. Note that B is n cross n. So B has n eigenvectors, right, and n eigenvalues. So let's say the eigenvalues of B are noted by mu's, right? So mu1, mu2 up to mu n. And let us say the corresponding eigenvectors are v1, v2 and up to vn. Okay, these are the eigenvectors corresponding to mu1, mu2 to mu n. Okay. Now A, being a bigger matrix, n plus 1 cross n plus 1 matrix, has n plus 1 eigenvalue. So it's lambda 1, lambda 2, we go all the way up to lambda n plus 1. Okay, these are going to be the eigenvalues of A. Now what I'm going to be interested in is how are the eigenvalues of A related to the eigenvalues of B. Okay, so let's try to apply the Rayleigh quotient theorem to A, right? So what does that say? It says that so long as I'm able to pick a unit vector x, then the value of the Rayleigh quotient is simply the same as the quadratic form x transpose ax is going to be between lambda n, lambda 1 and lambda n plus 1. Okay. Just going by whatever we did in the previous part, all I need to do is find an x, right, such that the quantity over here is very easy to evaluate, right, and hopefully that quantity happens to be one of the eigenvectors of B. Then I have an inequality that relates lambdas on the left and the right sides to mu in the middle. Okay, so that's what my plan is. My plan is to find an x such that the quantity here evaluates to the eigenvalues of B. Okay, fine. So to do that, first note that x is an n plus 1 cross n plus 1 length vector. So x is an n plus 1 length vector, right? Because A is an n plus 1 length matrix, x is an n plus 1 length vector, right? And these vectors over here, v1, v2 to vn, these are n length vectors, right? Because B is an n length matrix. Okay, so the natural inkling is, if I want this whole thing to evaluate to mu, that is the eigenvalues of B, I need to pick x to have something to do with the eigenvectors of B, right? So let me just pick x to be, let us say for now, v1, because v1 is only n length, but I want x to be n plus 1 length, I'll just do the most natural thing. I'll just pad it with a 0. Okay, so pad it with a 0. So x is n plus 1 length vector, v1 is an n length vector, and you get you just pad it with a 0 to get x. Okay, so let us just plug in this x into this expression, x transpose ax, and see what happens. First of all, x is a unit vector. It's very easy to see that because v1 being an eigenvector of B, typically without loss of generality, we assume eigenvectors are unit vectors. So it's a unit vector, adding a 0 doesn't change the norm, so this whole thing is still a unit vector. Okay, so x is a unit vector. So what I'm going to do is try to compute x transpose ax. So let's actually just compute ax first. It's very easy to see what ax is. So ax is going to be like b y transpose alpha multiplied with v1 0. We'll just multiply the block matrix as if they were regular matrices. So b gets multiplied with v1 plus y gets multiplied with 0. That gives you the first term, which is b multiplied with v1 is nothing but mu1 v1, because v1 is eigenvector of b. And the second entry is obtained by multiplying y transpose with v1 and alpha with 0, right? So that's y transpose v1 is the next step. Okay, so note that here what you get is not essentially so what you get here is mu1 v1. So the first n coordinates are simply a scaling of the corresponding n coordinates in x, right? But the last coordinate gets modified, so y transpose v1 may not actually be 0, it could be something else as well. Okay, now when we multiply again, so multiply x transpose ax. So multiply this quantity that we observed with v1 transpose 0, and you get mu1. Okay, when you multiply this time, the term here is just going to get multiplied with 0, so you're just going to be left with mu. Okay, so here is it. So here we have achieved our goal, so to speak, right? We were able to pick an x such that the corresponding Rayleigh quotient evaluates to an eigenvalue of mu, right? So just applying this theorem, the Rayleigh quotient theorem, tells you immediately that lambda 1 less than or equal to mu 1 less than or equal to lambda n plus 1. In other words, the smallest eigenvalue of b, that is mu 1, lies between the extreme eigenvalues of a. Right? Now there's nothing special about mu1. You could have done this with a v2 instead of v1 here. If you had picked a v2, you would have gotten mu2 here, right? And that could have given you lambda 1 less than or equal to mu2 less than or equal to lambda n plus 1. Okay, so basically what this tells you basically is that any eigenvalue of b lies between lambda 1 and lambda n plus 1. Okay, any eigenvalue of b, right? So if you had to actually visualize this on the number line, let's say this is your lambda 1 and this is your lambda n plus 1, right? The smallest eigenvalue, the largest eigenvalue, then all eigenvalues of b are going to be inside this region. Okay, all eigenvalues of b are going to be inside this region. So maybe mu1 may be somewhere here, right? And maybe mu n will be somewhere here. Okay, so basically what you're saying is that if you remove one row and the corresponding column from a matrix, the set of eigenvalues will in some sense compress, right? It will, so whatever earlier the eigenvalues were spread in this whole region, right, from lambda 1 to lambda n plus 1, now they're going to be spread within that region only. They're not going to spill out. I'm going to spill out of that region, right? So the smallest eigenvalue of b will still be above the smallest eigenvalue of a, and the largest eigenvalue of b will be below the largest eigenvalue of a. Okay, this process of course you can generalize even when you're removing multiple rows and multiple columns, right? So if I remove multiple rows and the same corresponding multiple columns from a matrix, then you can say that the set of eigenvalues will actually be within the earlier in the sense the interval, the span of the spread out of the eigenvalues will actually be within the spread of a. Okay. Now one exercise I just want to leave for those of you who are interested. Of course it's important to note that here you have a less than or equal to, right? So it's not necessarily strict, meaning that this gap over here can be 0, right? I mean, it doesn't have to be non-zero. Similarly this gap can be 0, right? So I'll just leave this as an exercise for you to think about under what conditions is lambda 1 equal to mu 1. Okay, meaning that suppose I don't want the smallest eigenvector to change, then what must happen, right? So that's the question. So I would request all of you to think about it. If you want to find the answer, if you want to ask me, you can do so in Piazza or on the live sessions. Okay, fine. So this is the examples that I gave are not necessarily very important or relevant, but they are very representative of the kind of use that the Rayleigh quotient theorem finds very, very, very often, right? Okay. Uh, as I mentioned before, one of the big practical applications of the Rayleigh quotient theorem is the principal component analysis, and if we have time in this segment, maybe we'll go through that in detail. Some material has already been shared with you, so I request all of you to go through that. And anyway, the AI students will be redoing PCA in one of their later courses of machine learning. What I'm going to talk about is one application to numerical methods in linear algebra. This is one of a very popular method called the power method. Okay, so the power method has to do with finding, let's say, the largest eigenvalue of a symmetric matrix. Okay. So basically the idea is the following, right? So often of interest is given a matrix, you of course want to find all of its eigenvalues, right? So how do we find all of the eigenvalues? Well, right now the method at your disposal is to use the definition, right? You start with Ax equal to lambda x, and then you try to solve this system of equations, see for which lambdas the system of equations has a solution, and you proceed in that fashion, right? That's how you do it. Some people may actually construct the characteristic polynomial, determinant of lambda I minus a equal to 0, and try to find the roots of the characteristic polynomial. Now remember that finding roots is not really very efficient. I mean, there are not standard techniques to find. There are standard techniques to find the roots of a polynomial, but so what we are going to discuss is a more principled way to find the eigen values of a matrix. There are many algorithms to find the eigenvalues of a matrix. I am going to focus on something that's very closely related to the idea behind behind the Rayleigh quotient theorem, or the variational properties of the quadratic form. Okay. So suppose if I want to approximate, just very quickly to recall, max of x transpose ax by x transpose x is lambda max, correct? So suppose if I want to approximate lambda max, then what do I want to do, right? So we all know that to get lambda max, you need to pick x to be equal to the corresponding eigenvector of lambda max, correct? So in order to obtain lambda max, all I need to do is somehow end up with an x, or somehow find an x such that x has a very large component along the eigenvector of lambda max. Okay, so let's call that eigenvector as v max. Okay, so try to pick an x that has large component along lambda max, along v max, sorry. Okay, so try to pick an x that has a large component along v max. So how do we do that, right? I mean, a priori we don't know what v max is, and how do I pick an x that has a large component along v max, right? So the power method uses a very powerful trick, right? So what it does, it starts with an arbitrary x naught. It doesn't matter what x naught is. Maybe x naught has components all over the place, right? It doesn't necessarily have component only along v max, but it's spread out along all the eigenvectors. Okay, so just to set out some notation, let us just assume that A has eigenvectors that are lambda 1, lambda 2 up to lambda n, right? And the corresponding eigenvectors are v1, v2 up to vn. Okay, and let us say I start with an x naught which happens to have components along maybe all of the eigenvectors alpha I, vi. Okay, ideally I would like v alpha n to be very large. I would like the coefficient of vn, that is the last term in the sum, to have a very large value, right? And all the other coefficients to have very small value. Large meaning large in absolute value, right? I don't really care about positive or negative at this point, right? So I need so to begin with, I'll just pick an x naught arbitrarily, so I don't really know anything about the alphas, right? Then here is what I do. Suppose if I apply, repeatedly keep applying a, that means let's say I apply a to the k x naught, okay? I apply a to the power of k times x naught, meaning I apply a k times. Now why do you do that? So remember, what does a do, right? The vectors, the eigenvectors get amplified by an amount is equal to the eigenvalue, correct? v1 gets amplified by lambda 1 when you apply a to it, right? v2 gets amplified by lambda 2 when you apply a to it, and so on and so forth. So vn gets amplified the most, right? So when you apply a many times, vn gets amplified so much that it almost completely dominates the other eigenvalues, the other eigenvectors. Okay, so that's the main idea, the main trick behind the power method. Okay, so a to the k of x naught, if we just actually just compute it, this is going to be summation of alpha I a to the k vi I equal to 1 to n. Okay, and then just because of the fact that vi is an eigenvector, a to the k vi, and most of you know this already, a to the k vi will actually be equal to lambda I to the k vi. Okay, basically when you apply a k times to the vector v, it gets amplified by lambda I k times, so that's why lambda I to the power of k. Okay, so lambda I to the k vi. Okay, so this is just going to be summation of alpha I lambda I to the k vi I equal to 1 to n. So the whole idea that we want to exploit is maybe lambda n gets amplified the most as compared to the other lambdas. Okay, there are many assumptions that I'm making implicitly here. I hope I'll clarify a lot of these as we move forward in the analysis. Okay, so let's just just to expand this whole thing out, this is basically alpha 1 lambda 1 to the k v1 plus alpha 2 lambda 2 to the k v2 plus so on, plus alpha n lambda n to the k bn. Okay, so now my claim is that this term is large compared to the other terms, so let's actually formalize that, right? How would formalize that? You will actually pick this lambda n to the k common, okay, and let us list the terms in the reverse order, right? So I'm going to list this term first. This term is going to be just alpha n bn plus alpha n minus 1 times, here is what is going to be lambda n minus 1 by lambda n whole to the k. Okay, vn minus 1 plus alpha n minus 2 lambda n minus 2 by lambda n to the power of k vn minus 2 plus so on, all the other terms that are going to be involved in this expression. Okay, now the main idea here we want to say is, if k becomes very large, as this term k becomes very large, I want all these other terms to die out and I only want this term to remain. Okay, because ultimately I only want the nth eigenvalue to remain. I don't really want to compute the other eigenvalues at all, right? I only want to compute the nth eigenvalue. So all these terms must die to 0 as k goes to infinity, and for that to happen, these quantities over here inside the exponent must be within minus 1 to 1. Okay, so lambda n minus 1 by lambda n must be between minus 1 and 1. Okay, so if it's let's say 0.5, then when you do 0.5 to the k, 0.5 square, 0.5 cube, you get smaller and smaller numbers, right? It could be negative 0.5 also, right? If it is minus 0.5, then also you get smaller and smaller values as your k keeps on increasing, right? So what we want is, we want the absolute value of lambda n minus 1 by lambda n to be smaller than 1. Okay, so note how it's important that the absolute value is smaller than 1. I don't actually care. I don't just want lambda n minus 1 by lambda n to be less than 1. I want the absolute value to be less than 1, right? And similarly lambda n minus 2 by lambda n to be less than 1, and so on and so forth. I want it to be true for all the eigenvalues. Lambda 1 by lambda n, absolute value to be less than 1. Okay, in fact the more these absolute values are lesser than 1, the faster these terms will all go to 0, correct? For example, if this quantity here is 0.99999, Even then, as k goes to infinity, this term will go to 0, but it will go so very slowly, right? As opposed to when this ratio is, let's say, 0.1, then this term goes to 0 much faster. Okay, so the smaller they are than 1, the faster the convergence is. Okay, what this means is I effectively want lambda n to be bigger than the absolute value of all the other eigenvalues. Okay, in other words, I want lambda n is the largest eigenvalue in magnitude. Okay, not just as a real number but in magnitude. Okay, so you'll see that what the power method does is it actually gives you the eigenvalue that has the largest magnitude. It doesn't care if it is positive or negative, right? In fact, it could be the smallest eigenvalue, okay, but the largest eigenvalue in magnitude. That's what the power method gives. Okay, so what is happening over here? Let's just summarize this discussion. Under these assumptions, okay, under the assumptions that I stated here, right, what happens is that all the terms in this expression go to 0 except one term, right? So what are we actually computing here? We are finding a to the k x naught. So to summarize, we started with an arbitrary x naught, apply a many times, okay, and then we are saying that if you apply a enough number of times, you will just be left with the largest eigen vector. All the other components will actually be close to 0. Okay, so this is how you would write it. You would say that a to the k x naught is very close to, so let's just look at the expression here, lambda n to the k alpha n bn. Okay, it's very close to lambda n to the k alpha n bn. So note that here these quantities are just scalars, right, and this is a vector. Okay, so what this gives you is that a to the k x naught will approximately be along the direction of Vn. Okay, so that actually tells you immediately what Vn is, right? So you say that Vn is unit vector along the direction of a to the k x naught. Okay, Vn is the unit vector along the direction of a to the k x naught, or to write it precisely, you can do like this: a to the k x naught divided by absolute value of a to the k x naught. Okay, so this is the idea behind the power method. It actually tells you how to find Vn. Once you find Vn, can you guess how to find lambda n? How do you find lambda n once you know Vn? We'll just do Vn transpose a Vn. Okay, that tells you how to find lambda n. Okay, you simply find the corresponding quadratic form, and that will allow you to compute lambda n. Okay, so this is an algorithm. It's probably one of the early and still very powerful algorithms to find the eigenvalue of the largest magnitude. Okay, so to find the eigenvalue of the largest magnitude, so you can use this algorithm to do so, right? Now to analyze any algorithm, you actually need to look at the complexity of the operations involved in that algorithm, right? So how many computations are you actually doing, right? So it might seem that for this algorithm to work, I have to actually compute a to the k, take a to the power of k, multiply it with x naught, and that seems like a lot of work, right? Because taking a matrix power is probably very expensive. We can actually find out the computational complexity involved in that, right? But you don't actually have to take the matrix power, right? You can actually approach this in an iterative fashion. For example, let us say you have computed a square already, then you don't have to recompute a cube from scratch, right? Because a cube is just a square times a, so you can make use of that information, right? So this essentially gives you an iterative algorithm to find the largest eigenvector. So what you do is start with an x naught. Okay, so start with an x naught. Okay, and then what you do is define xk to be a times x naught by absolute value of a times x naught. Okay, so sorry, a times xk minus 1, just rewrite that, xk minus 1 by absolute value of this. Okay, so so for k equal to 1, 2, 3 and so on, so right. So this is an iterative way, basically, just like how you do powers, right? It's the same iteration. Xk is a times xk minus 1, so at k equal to 1 you will get ax0 by norm of ax0. It's simply as if you put k equal to 1 over here. Okay, so define this to be xk, then one can check that xk converges to the Vn, the eigenvector corresponding to the largest eigenvalue in magnitude. Xk converges to Vn as k goes to infinity. Okay, and xk transpose axk converges to lambda n as k goes to. Okay, so that's the idea behind the power method. Now a couple of very quick notes that I want to make. What are the issues, right? Of course, the first thing that I mentioned, it only gives you the largest eigenvalue, the largest eval in magnitude. Okay, it doesn't give you the other eigenvalues. It may not even give you the largest eigenvalue. For example, if symmetric matrix has eigenvalues like -5, -4, 2 and 1, okay, the power method will give you -5, and it will give you the corresponding eigenvector, the eigenvector corresponding to -5. Okay, so that's one thing, but there are workarounds. Okay, there are workarounds to find other, there are workarounds to find other just one second, there are workarounds to find other eigenvalues and eigenvectors as well. Okay, to find other eigenvalues, we may try to explore some of these in the practice problems. Okay, the other issue is let us say the the computations and rate of convergence. Okay, let's look at the computations involved here. So each step I have to find xk, right? This is the key step in the algorithm, right? To find the largest eigenvector, I have to find xk. So all I have to do is I have to do matrix multiplications here, right? So if this A is an n cross n matrix, to compute this will roughly take me O(n) square computations, right? Order n square computations. Finding the norm, once again, is just going to be order n on top of order n square, so it's still order n square, right? Because axk minus 1, once you finding its norm is just going through the whole array once and taking square and taking square root, right? So this whole thing costs you order n square operations, right? Similarly here, once you have axk, right? So this is xk transpose, I'm sorry, typo here, xk transpose. Once you have xk, once again finding this dot product between xk and axk is again going to be order n. Okay, so this whole operation is going to just cost you order n square. Okay, but that's just one iteration, right? For one value of k. If you take more and more values of k, you have to do more and more. So the computations required is order n square per iteration. Okay, and the number of iterations depend on the speed of convergence, right? How fast does it converge? As I told you, speed of iteration depends on the ratio, these ratios, right? Lambda n minus 2 by lambda n and so on and so forth. Okay, if these ratios are far away from 1, then the iterations actually converge very, very fast. Okay, so in one of the tutorial problems, I'll leave sort of an assignment for you to do. Either you can do it by programming or you can just do it by hand with a small matrix example, just to see how fast it converges in particular scenarios. Okay, so computations are order n square. However, I do want to highlight here that this order n square computations are for an arbitrary matrix A, for a generic matrix A, right? Oftentimes there is a lot of structure on A, right? For example, A could be a very large matrix, meaning n could be like a million, but it could be very structured, meaning that maybe it's very, very sparse, right? Maybe A is a very large matrix, but only few coefficients are non-zero. in which case computing this quantity axk minus 1 will not take you order n square. It may actually be way faster than that. Okay, depends on how sparse a is. Okay, so in that case the algorithm here will actually converge, will actually take even lesser number of computations. Okay. The third thing I want to highlight here is that we made an implicit assumption in all these calculations here. If you go back to this expression, we said that this gives me a vector that is along the direction of Vn, right? That's of course assuming that this coefficient is non-zero, right? So remember, what I'm doing eventually is I'm actually taking this vector and I'm dividing by the norm of that vector. Okay, so I need to be able to make sure that whatever I am dividing by is not zero, not small. In other words, I want to make sure that this quantity is not small. Okay, because this is effectively the magnitude of this vector, correct? Because Vn is a unit vector. Lambda n of course is not 0, because lambda n we already assumed is the eigenvector of the largest magnitude, so that cannot be 0. If lambda n is 0, the whole matrix might as well be 0, right? The only thing is you have to make sure alpha n is not 0. Just recall what alpha n is. Alpha n is the component of x naught along Vn, right? Alpha n is the component of x naught along Vn, right? So this is basically the term here, right? So you need to make sure that your initial x naught must have some component along Vn. In other words, x naught must not be perpendicular to Vn. Okay. So that's how you need to pick x naught. So often what you do is you pick x naught randomly, right? If you pick a vector randomly, it's very likely that you will not end up picking something that's perpendicular to Vn. Okay, fine. So this is what I wanted to say. So the important thing to reiterate is that it finds the largest eigenvalue in magnitude. By the way, that is something that's called the spectral radius of a matrix, right? The spectral radius of a matrix is the largest magnitude eigenvalue, largest magnitude of eigenvalues. Okay, take all the eigenvalues and pick the eigenvalue of the largest magnitude. For example, here in this scenario, when you had a matrix whose eigenvalues are -5, -4, 2 and 1, the spectral radius is 5, right? Spectral radius is 5. So what the power method does is finds the spectral radius and tells you the eigenvector corresponding to the spectral radius. Okay, in the next lecture we will look at a generalization of the Rayleigh quotient theorem and some very interesting consequences of that.